Alright, hello everyone. I hope all of you are doing great. So this is going to be a video after a very long time. Well, I had my reasons, but I'll try to make sure that breaks like these don't happen in the future, right? I'll try to be more regular, and with that in mind, today we are going to be discussing the solutions to Codeforces Educational Round 139, and we'll be discussing the first 4 problems from A to D. Talking about the round, I think the first 4 problems were quite doable this time. So problem D definitely was easier than a typical Div 2 D or a typical Edu round D, right? And I will also say that problem C was a little bit easier than a typical Div 2 C or an Edu round C. Otherwise, the round wasn't bad at all. There were no particular issues with problems as in the last round, right? So yeah, overall a pretty smooth round. I was quite close to solving E, but I couldn't really get it. So yeah, we'll be discussing the first 4 problems. Let's start with the first problem A. So it's called extremely round, and here we have the definition of an extremely round integer, and an integer is extremely round if it only has one non-zero digit. For example, all these numbers have just one non-zero digit, so they are extremely round numbers. Now we are given an integer n, and our task is to calculate the number of integers, the number of positive integers which are smaller than or equal to n, which are also extremely round. So yeah, this is the problem. It's pretty easy, I guess. So let's just quickly discuss the solution. So the main observation here is that we know that for any round number there will be exactly one place which will be non-zero, right? So if the non-zero place, if the non-zero digit is not the most significant digit, right? So if the non-zero digit is not the most significant digit, then it doesn't matter what it is because it will still be smaller than n, right? So it's not the most significant digit of n, right? So in that case, the number will always be smaller than n no matter what digit we place. So in this case, we have 9 possibilities for every place, right? And for the most significant digit, we can only have a number. We can only have a digit which is smaller than or equal to the most significant digit of n, right? So for most significant place, we can only have digits which are smaller than or equal to the most significant digit of n itself, right? And that is it, right? So in hindsight, the solution is that if the length of n is, let's say, m, so if length is equal to m, then the answer is nothing but 9 into m minus 1, because there are like m minus 1 places which are not the most significant places, and there is one most significant place. And let's say that the most significant digit of n is x, then or maybe let's say it is d, then we can have digits from 1 to d at this place. So we'll just add a d here. So this is going to be our answer, straightforward. So yeah, that's the solution. Let's just have a quick look at the code. The code is pretty simple. We read in the number n as a string just to make things easier, and if n is the length of the string, then the answer will be 9 into n minus 1 plus s of 0, which is the most significant digit, right? So yeah, this is the solution to problem A. Now let's move on. Now we'll talk about problem B. Okay, so this is an interesting one. So what we have here is that we want to type a string s consisting of n lowercase Latin letters. We are provided with the string s, and we are using a text editor which provides us with the following options. And the options are that we can append any letter to the end of the string which we have already typed. This is the first option. The second option is that we can copy a continuous substring of an already typed string and paste this substring to the end of the string, right? So I hope these options are pretty self-explanatory. So the second option basically means that we have a string which we have typed till now. So we'll just choose any contiguous substring. We are allowed to choose any substring, and in one operation we can paste that entire substring towards the end of the string which we already have till now. Okay. Now what is our job? Our job is to tell, can we type the string s in strictly less than n operations? We don't have to find the minimum number of operations. All we are interested in is telling whether or not it's possible to type the string in strictly less than n operations, right? Cool. Now let's have a look at the solution. So the first thing which we can note here is that if we only use the operation of type 1, so if we only use operations of type 1, in this case we will make exactly n operations, right? We need exactly n operations. So if we only use operations of type 1, we will need n operations, and we can't do it in less than n operations using only operations of type 1. Okay, so that means our requirement boils down to using at least one type 2 operation. So we need at least one type 2 operation, and that too, in that type 2 operation, the substring which we are pasting should be greater than or equal to 2 in length, and the substring that we paste should have more than one character, right? So this is the requirement. The reason being that if we just paste a substring of one character, it is like doing the same thing as operation 1. It is exactly the same thing, right? So we are getting a benefit of only one, whereas we need a benefit of more than one in at least one operation. And if we do that, then we will type the entire string in strictly less than n operations, right? So I hope the requirement is clear. Now if we look carefully, what happens is that we can basically iterate on the first time we use this type 2 operation, and we'll try to analyze what are the required conditions. So we iterate on the first time we use the type 2 operation, right? So we try to iterate on this and we check whether or not it's possible, right? And check whether it is possible. If at some point we find that at a particular index we can use the type 2 operation to type more than one letters, then basically we are done. Okay, so let's say we are currently at the ith character and we are trying to check whether we can use the type 2 operation here or not. Okay, so we have a string like this, and this is where we are right now. And this is the substring which we have already typed. So this is the substring which we have already typed, and this is the substring which we need to type. So let's say this is index I and this is index I plus 1. Now if you notice carefully, what we want is we want to use the operation of type 2 here. Okay, we want to use the operation of type 2 at the ith index. Now what are the necessary conditions to do that? So the necessary condition is that we should have, so basically we need to type these characters from, okay, so we need to type si, si plus 1, si plus 2, and so on. But we need at least two characters in one go, because that is how we'll be winning, right? We need at least two characters to win. Now how will we do that? So if we look at only si and si plus 1, so if we are typing more than one character, then we are at least typing si and si plus 1, which means that in this portion where we have the already typed characters, there should be a substring which is exactly this, si and si plus 1. Because if this is not present, then forget about typing substrings of length more than 2. Because for any substring of length more than 3, let's say we type si, si plus 1 and si plus 2. In that case, we'll need a substring si, si plus 1, si plus 2. But still we need a substring si and si plus 1 to do that, right? So the requirement boils down to we need si, si plus 1 to be already present. So there should be an index j. There should be an index j which is strictly less than I minus 1, such that sj is equal to si and sj plus 1 is equal to si plus 1. So if this is possible, if we find a j for any I, then we'll straight away output yes, otherwise we'll output no. So this completes the solution. The implementation is pretty easy. There are multiple ways we can implement this. I'll just show you guys how I did it. So this is what I did. I used a set of pair of characters. So for every I just inserted si and si plus 1 into my set, and then I check whether I find this particular, for a particular index I will check whether or not si plus 1 is already present in the set. If it is already present, then I'll straight away output yes. Otherwise, I'll be inserting si minus 1 and si into the set, and I'll keep iterating, right? So yeah, this is the solution to problem B. Okay, now let's move to the third problem. Alright. Okay, so in this problem, basically what we need to do is there is a grid of 2 rows and n columns and 2 rows and m columns, and what we want to do here is that some of the cells are painted white and initially all the cells are painted white and we need to paint some of the cells as black. It is provided to us which cells need to be painted as black. Now what we need to tell is we need to tell whether or not there is a path which covers all the cells which need to be painted black exactly once, and it does not cover any cell which is painted white. And as always, the path like between two adjacent cells of a path, there should be at least one common side, right? So yeah, we need to tell whether or not such a path exists. Also, there is one more constraint, that in every column there is at least one cell which needs to be painted black, right? So yeah, I hope you guys understand the problem. Now let's move to the solution. Okay, so this problem basically is a pretty simple dynamic programming application. So let's see what's happening here. So we have a grid like this. Some of the cells need to be painted black, some of the cells need to be painted, some of the cells are already white. I mean, all the cells are already white, but some of them need to be painted black. All we need is a path which starts from a black cell and ends at a black cell and covers all the black cells exactly once without covering any white cell, right? Okay, let's say we have a random grid like this. Okay, so what we want to do here is we want to define a DP state with which we can solve the problem. So let's say we use this state dpij. Can we start from ij? So only considering columns from j to n, obviously. So only considering columns from j to m. Can we start from ij and satisfy all the conditions? Right. So this is my simple DP state. I am sure there are other solutions or there are other methods with which we can do it. For example, if we only consider columns from 1 to j, I mean, it's all pretty much the same thing. But this is what I did. Right, so this is my dpij. It's a vector of Boolean values where it is true if we can start from ij and visit all the black cells exactly once and reach the last column, and it's false otherwise, right? So what will be our final answer? So final answer will be dp11 or dp21, right? Because in the first column we'll check both the cells and we'll check both the cells dp values. If at least one of them is true, then it's possible to do it, right? So this is going to be our final answer. Now let's just have a look at the transitions. The transitions are also pretty simple. So what's happening here is that let's say we are at I comma j, and case 1 is that cell I comma j is white. So cell I comma j is white. In this case, obviously, since we can't iterate on any white cell in our path, we'll just simply say that dpij is false. Okay. So this is case 1, pretty simple. Let's just look at case 2. So case 2 is that now we know that our cell is black. So aij is black. Now we'll look at a ISOR1 j, right? ISOR1 just means that we are looking at the cell which is in the same column but in the other row, right? So for example, if this is ij, then this will be ISOR1 j, right? Cool. So if now if a ISOR1 j is also black, then what happens? So if a ISOR1 j is also black and we are starting at I comma j, then we are bound to go from I comma j to ISOR1 comma j here. And once we are here, since we can only visit cells once, we are bound to go here, right? So this is the path that we will be bound to take. So that means from ij, we'll be going to ISOR1 and j plus 1. So we'll simply assign dpij. If it's possible to reach from ISOR1 j plus 1, then it's also possible to reach from ij. So dpij will be dp ISOR1 j, right? So this is case 2. and case 3 is when aij is black but ai's or when j is white, right? So aij black, ai's or when j is white. Now in this case, if we look here, okay, so let's say that this was black. Now we are at a case where aij is black but ai's or when j is white. So now since we can't visit any white cell, we are bound to go from here to here. So from ij we will be going to ij plus 1. Okay. So it's pretty simple. dpij would be equal to dpij plus 1. And this is it, right? These are all the cases and the solution is pretty much complete. I think this was pretty simple. Let's just have a look at the code. Okay, so as usual we have this dp vector and these are the initial values dp1n. If a1n is equal to 1, which means that, so here 1 is denoting white and 0 is 1 is denoting black and 0 is denoting white. So if the cell in the first row and the last column is black, then dp1n would be true. Same for the second row and last column. Now we look at all the columns other than the last column, and the transitions are pretty much the same as I had already written, and the final answer is going to be either dp11 or dp21. Okay, cool. So yeah, this finishes problem C. Let's now look at the last problem, problem D. Cool. Okay, so let's see what we have here. So in this problem, let's define a chain induced by x comma y as a sequence of pairs xy, x plus 1 y plus 1, x plus 2 y plus 2, and x plus k y plus k. So this is a chain, and for some integer k greater than 0, the length of this chain is going to be k plus 1, obviously, right? Now a chain is called lucky. So a pair of positive integers is called lucky if their GCD is equal to 1, right? Now in this problem, what we have to do is we are defined a lucky chain. So a lucky chain is a chain such that all the pairs in the chain are lucky. That means all the pairs in the chain have GCD equal to 1 or are co-prime. Okay. Now we are given n pairs, and what we need to do is we need to calculate for each pair the length of the longest lucky chain which is induced by this pair. Okay. So we'll start from xi yi and we'll look at xi plus 1 yi plus 1 up till so on, and we'll try to find out the biggest chain such that all the numbers still remain co-prime starting from every xi comma yi. Right. Cool. So I hope the problem is clear. Also, it's possible that xi and yi are itself not co-prime. In that case, the answer is going to be 0. And it's also possible that this chain is infinite, that is, it never ends. So for all values of k, xi plus k and yi plus k is co-prime, it might be possible. In that case, we need to output -1. Okay, cool. I hope the problem is clear enough. Okay, so let's just get rid of the first few cases straight away. So the first case is that GCD xi yi. So GCD xy is not equal to 1. So in this case, we will straight away say that the answer is equal to 0 because the chain will never be formed. And the second case is that absolute value of x minus y is equal to 1. In this case, what happens is that x plus 1 and y plus 1 still has the absolute value of x minus y equal to 1. So we are never changing the absolute value, and it's a well-known theorem that for any two consecutive numbers, there is no prime factor which is common to them. So in this case, the answer is going to be -1. Okay, cool. So these are the trivial cases. Let's just get them over with, and let's now start with the solution. Okay. So how to solve this problem, right? So we need to look at, starting from x comma y, what is the first value of k when GCD of xi plus k and yi plus k will not be 1. So we need the smallest k such that GCD of x plus k and y plus k is greater than 1, right? Now what does this mean? What does it mean that GCD of x plus k and y plus k is greater than 1? It means that there is at least one prime number which divides both of them, right? So there is at least one prime number which divides x plus k and y plus k, right? Okay, so if we have this intuition, then there is a very easy naive solution. Of course, it would be inefficient, but we have a naive solution, right? So what we can do is we can iterate on all the primes and for each prime p, find out. So as you can see, the constraints xi and yi are up to 10 to the 7. So we'll look at all the primes which are less than equal to 10 to the 7, and we'll find out for each prime p the smallest k, such that x plus k and y plus k are multiples of p, right? If we can do this, then the problem will be solved, but obviously the number of primes smaller than or equal to 10 to the power 7 is a lot. So there is another theorem in mathematics and number theory that for a number n, the number of primes which are smaller than n is of the order n over log n. So if we look at 10 to the power 7, there are around like 5 into 10 to the power 5 prime numbers. So, and the number of queries that we have is 10 to the power 6. So if we try to naively do this, then this is going to TLE, right? So now we somehow need another observation, right? So what will be this observation? So the main observation here is that if p divides both x plus k and y plus k, then p will also divide y minus x, assuming that y is greater than or equal to x without loss of generality. So we'll assume that y is greater than or equals to x. If that is not the case, then we can swap xy, right? So this is something which we do right in the beginning of our code. So from now on, I assume that y is greater than x, right? So if p divides both x plus k and y plus k, then p will also divide y minus x. Now why is that true? That is true because if p divides x plus k, then x plus k modulo p equal to 0 and y plus k modulo p equal to 0. So if we subtract these two, if we subtract 1 and 2, it's also a very well-known theorem actually, but for the sake of completeness, I'll just prove it. So I'll subtract 1 from 2 and we get y minus x modulo p is equal to 0, right? So this way we have proved that for a prime number to divide both x plus k and y plus k, that prime number has to be a factor of y minus x, right? Cool. So now we know that we only need to look at prime factors of y minus x, right? That's all we want. Cool. So now we are really close to the solution. The only key which is missing here is that how do we find the smallest k such that x plus k and y plus k are multiples of p very quickly, right? So now this is pretty easy. All we need to do is we need to look at this value. So we need to look at x modulo p for any prime p. We need to look at x modulo p. So initially, let's say that x modulo p is equal to r, right? So as we increase x, what happens to the modulo? The modulo decreases, right? So the modulo also increases, right? So the modulo will be r for x, and x plus 1 modulo p. X plus 1 modulo p would be r plus 1, and then we'll get r plus 2, so on and so forth, until we get the remainder as p minus 1, and eventually we'll get a remainder of 0, right? So this is what is happening. So how many times do we have to increase to get a remainder of 0? It's pretty easy to calculate. It is nothing but p minus x modulo p, right? Because initially the remainder is x modulo p and it increases by 1 in every step, and we need to get it to p because p modulo p is equal to 0. So the number of steps that we need is p minus x modulo p. So all we need to do is iterate on all prime factors of y minus x and take the minimum value of p minus x modulo p. Why we are taking minimum value? That's because once we reach this particular value of k, p minus x modulo p, the prime number p will divide both of them and the chain will be broken. So that is why this is going to be our answer. The only thing which is left now is to figure out how do we actually find out the prime factors, because the numbers are really large. So the numbers are 10 to the power 7. So we can't really pre-compute all the prime factors. We have to factorize it on the go. So it turns out that there is a very clean way to do this using sieve. So the way we do this is we compute the smallest prime factor of every number beforehand. So we pre-compute this, and using these values, factorize a number in O of log n time. We can spend O of log n time per query because the time limit is 4 seconds, so I think that's pretty alright. Right, so this is what we have to do. This technique is pretty well known, that is why I'm not elaborating on it, factorizing using Ceph. So I'll just leave it as an activity for you, leave it as an exercise. If you don't know it, go on the internet and try to search how we can factorize numbers using the smallest prime factor, right? So this is the solution to problem D. Let's just have a quick look at the code. So this is how we actually do this. We first compute the smallest prime factor of every number using Ceph, and this is the factorize function. We just keep dividing the number by its smallest prime factor until and unless the number becomes 1, and this way we can get all the prime factors. So this factorize function will return me a vector which contains all the prime factors of n, right? So now we read xy. If GCD is not equal to 1, we output 0, and if difference is equal to 1, then we simply output -1 because there will be no prime factor, which will be a multiple of x plus k and y plus k, which will be a factor. And then we generate all the prime factors of this difference y minus x, and we just take the minimum value of p minus x modulo p, and that is going to be our answer, right? So I hope this makes sense to everyone, and this is all that I had to discuss today. Thank you so much for watching, and I'll see you in the next video.